So this is class 18, and we are really making progress. I don't know if you realize it, but there are only 28 lectures in the semester. Well, not less than that, because 2 of our class meetings are for exams. And so really, there's only 26 lectures. So we're at 18 out of 28. So we're well past the halfway point right now. We're making good progress, finishing up chapter 4 today, and then on Tuesday we begin chapter 5 in the book. Tuesday is when homework 7 is due, and I know that several of you have already started working on that assignment because I've got some good questions by email. We're going to continue, we're going to talk about irrotational flow today, and so the last couple of problems in the homework assignment are related to that. So today we're going to discuss irrotational flow and centripetal acceleration. And there are 3 videos that I'm going to be showing you today just because they are nice illustrations of concepts, and kind of the animation makes the point in a way that just my talking wouldn't really be able to do. So I think we had pretty good luck in the past with the audio coming through, but if you can't hear anything, please do let me know. So this first video is talking about the difference between centripetal acceleration and centrifugal. What we're going to be talking about today is how an acceleration changes the pressure and elevation of fluid. And you could say that that same thing is true with Bernoulli's equation and Euler's equation, because remember, Bernoulli's equation describes a convective acceleration and the effect that it has on pressure, the relationship between pressure, elevation, and velocity. And Euler's equation, which describes local acceleration and the effect that it has on elevation and pressure. Those 2 acceleration types are really important for describing how fluids behave in the world. And when fluids are experiencing a radial acceleration, then we have a different set of equations that can tell us the relationship between pressure and elevation for those as well. And so the tangential velocity of a particle that's experiencing circular motion. And so in that video that we just watched, they talked about a can that was going around in a circle. And if we assume that there's a fluid inside of that can, then the acceleration that's occurring because of the change in direction of velocity is going to cause a difference in pressure inside of the can that isn't described just by the hydrostatic equation. There's some other pressure relationship that we need to be able to predict. And so even if the can or a particle is going around in a circle at a constant speed, it still has acceleration because the direction component of the velocity is changing. Remember that as a vector, velocity has both magnitude and direction. And if either one of those change, then it must be an acceleration that's causing that change in velocity. So in the case of a radial movement of a particle, if it's going in a circle, then there's an acceleration inward towards the center. And so here the A sub c is talking about the centripetal acceleration. And so omega, the Greek symbol omega, is talking about the rate of rotation. And the units for that are radians per second. And of course we know that in a single rotation there are 2 pi radians. And so radians per second describes how quickly it's going around through that circular pattern, and r is the radius of curvature, and so it would be the distance between the center axis of rotation and where the object in question is located. So you can determine the tangential velocity by multiplying the radial acceleration and the angular velocity omega and the radius. Now, the radial acceleration can be found in one of 2 ways. Either you take the angular velocity and square it and multiply it by the radius, And if you consider the units there, one important thing I need to mention, you'll notice that for the angular velocity of radians per second, in the SI unit system, radians isn't considered one of the base units. And so it's almost as though the radians aren't there. It's not a real unit. So we know that acceleration has units of meters per second squared, right? Whether it was local acceleration or convective acceleration, or in this case, the radial acceleration, the units of acceleration are always length per time squared. And so if you look at this omega squared times r, the way that we get meters per second squared from that is that there's meters in the radius, and then the inverse second squared comes from omega squared, but there's no radians carrying through in that units. And so when you're doing these centripetal calculations, you kind of just ignore the radians in the units. And I know that's complicated, but it's a whole rabbit hole that we could spend the rest of the lecture on, the handful of units contradictions that exist in the SI system, and this is one of them. So that's one way to determine the radial acceleration. Another is the tangential velocity squared divided by the radius of rotation. And so if you know the speed at which the particle is moving around in a circular manner, square it and divide by the radius of rotation, then from that as well you get units of meters per second squared. So the centripetal acceleration is inward towards the center axis of rotation. The effect that it has on a fluid is demonstrated in this next video. So what you can see is that the fluid is rising in the outside edges. As it's spinning in a circle, the acceleration, which is inward towards the center, and is causing the fluid to rise in the outside edges. And let's think if there was any kind of commonality with that and what we'd had before. Remember that in the case of a local acceleration where we're using Euler's equation, the pressure of the fluid increases in the opposite direction of acceleration. Or if it was a container of water, like remember the truck that was carrying gasoline, and it sloshes, the liquid sloshes on one side, and so if you accelerate it to the right, then the liquid level increases on the left. And a similar thing is true here, where the acceleration is in towards the center, but the liquid level is increasing outward and further away from that center. And so what we said before is that the pressure or elevation increases in the opposite direction of acceleration, and that same thing is true even when we have centripetal acceleration. So they'll slow this down in a minute, show a high-speed camera. So as it's being accelerated, you can see that the fluid level is increasing on the outside. Both the width of the aquarium and the depth of the aquarium. You can see here from this side view that the liquid level is higher on the edges than it is in the middle. And that's because the edges are further away from the central axis. You know, if you just think about a top view of a rectangle, it's the outside edges that are the furthest away from the center. And so that's where the radius is the largest. Okay, I think you've got the idea that what we need is some sort of an equation that is going to describe the relationship between the acceleration that's being experienced and where the water is in an open tank like this. But think, what if this tank had a lid on it? You know, what if there was a glass lid that was right up to the level of the water? In a case like that, the water wouldn't be able to deflect like it is now because it can freely move since it's just air above the water. If there was a container, then the pressure would be affected, but the physical elevation of the water would be unaffected. And so that's similar to what we saw with Euler's equation, where if it's an enclosed tank and we're accelerating the enclosed tank, the pressure changes, but the liquid level doesn't. If it's an open tank and there's just air at the interface of the liquid and the gas above it, and you accelerate the tank, then the liquid level shifts as well as the pressure. So we're going to have some similar analogies in what we go through today. Now, sometimes in problem statements, you'll be given the rotational rate, not in radians per second, but they'll be defined in revolutions per minute, RPM. And so 1 revolution, of course, is 2 pi radians, and there are 60 seconds in 1 minute. So if you are given how quickly something is spinning in terms of RPM, revolutions per minute, and you need it to be in units of radians per second in order to calculate, for example, the acceleration. So if you need it in radians per second, then you should multiply by 2 pi and then divide by 60. And that's the applicable unit conversion from RPM to radians per second. All right, so in the previous video, we saw the shape of a water vortex. And we'll look at just one more quick video today. This is one that you could make at home with a couple of 2-liter bottles. So you can see that there's a little bit of a spinning just to get things going. And then as the water is falling downward because it's draining, then its rotation continues. That's a pretty good vortex there. And so this is rotational flow. Rotational flow when the liquid is going in a circular manner rather than at a constant velocity forward or accelerating forward due to a local acceleration. This is a different type of acceleration. And so the equation that we're going to look at today allows us to describe the shape of this surface based on the acceleration that the water is experiencing. And so we want an equation that will tell us between 2 points what's the elevation change and what's the pressure change. Now, to learn the equation and apply it for some initial problem solving, what we're going to do is consider the water level inside of a U-shaped tube. And so let's just consider that this is like a container of some sort. It could be made up of glass or plastic or anything at all, really. The diameter is large enough that we don't have a capillary effect that is playing any role of the liquid surface. But what's causing a deflection in the liquid surface is the fact that this is rotating about the left leg. So you can see that there is a higher water level on the right and a lower water level on the left. And the reason why it's higher on the right is, remember that the liquid level increases in the opposite direction of acceleration. And so the fluid, the acceleration is in towards the center. So here's the center, and so the water here on the right leg is accelerating towards the center, and the elevation increase is in the opposite direction. So you can see some dimensions here. We're talking about a deflection of 25 centimeters, and that means that the elevation values are different between the left leg and the right leg. There is a radius that's defined of 10 centimeters, and so with the radius, that's going to enable us to determine the magnitude of the acceleration. So here is the formula that we use to describe the shape of the water surface when there's an acceleration in a rotational way. This maybe looks a little bit like Bernoulli's equation at first glance until you see that third term. So this is for sure, this is not the Bernoulli equation. This is something separate. What this says is that the pressure head, P1 divided by gamma, and the elevation head, and then minus the rotational rate squared times the radius squared divided by 2g, that the sum of those three terms, when combined together, is equal to the combination of those terms at location 2. And so the way that we usually apply this is we pick location 1 and location 2 at locations where we know a lot of information, because ordinarily what we're going to do is substitute in the known values into this formula and be trying to calculate some unknown value, like, for example, how high the water rises, or at a certain location, what's the pressure. So that's our typical approach. And in this case, what we would do is we would say location 1 is here at the left leg, at the interface between the water and the air that's in the tube. You can see that the tube is open at the top on both sides, and so it's just atmospheric air inside of here. So there's zero pressure at the interface on the left and on the right. So this is location 1, here is location 2, and we know a lot of things about those two locations. For example, we know that at 1 and at 2, the pressure is 0. So what that allows us to do is to cancel out the pressure terms. And if we set the elevation datum to be this left water surface, so we said Z1 is 0, then we could say that Z2 is 0.25 meters, because we know the elevation difference between them. And here location 1 is right on the axis of rotation. So R is talking about how far is your location from the center point about which everything is rotating. And so location 1 is just right on the axis of rotation. And so that means that R1 is 0. And R2, the radius over to location 2, is 0.1 meters. So in the end, in this formula, we know everything except for what's the rotational rate that's causing this deflection. And so let's get some experience plugging numbers into this equation and kind of getting a sense for how it works. This is water that is inside of this U-shaped tube, and we want to find out what is the omega. That's the rotational rate in radians per second. And so you'll get that by substituting in on and making the cancellations that we were talking about in this formula. So let me pause for a second and see if you can calculate what is the radians per second that this is rotating. It's spinning at a certain radians per second that's causing this liquid level to rise on the right side. So find the rotational rate, and then when you have that rotational rate, the radial acceleration. And just to refresh your memory for the formula, let's go back to this earlier slide. I'll copy and paste that into the example. All right, so you're going to use this equation for part B, and also for part C to find the tangential velocity. All right, so let me stop for a second and have you start making substitutions and solving for omega. And then we'll get back together and make sure that we all have the same numbers. Has anybody found the rotational rate yet, omega? If you do, type that into the chat box. Anybody? Omega? That's right. Very good. Thank you, Brandon. All right. So let's look at this together. Yes, Eric, that's right. If you look at the equation, all of these, like the pressure, the elevation, the radius, have subscripts 1 and 2, but the omega doesn't, because at both locations it's rotating through the same number of radians per second. All right, so the cancellation here, if we have location 1 on the left at the interface of the air and the water, location 2 on the right at the interface of the air and the water. So here's the full version of the equation for rotational flow, and what we're saying is we know a lot of things at 1 and 2. We know that the pressure, the radius, and the elevation at location 1 is 0. That cancels out all 3 of the terms on the left-hand side of the equation. We also know here at location 2 that the pressure is 0 and the elevation is 0.25 meters above what we said was going to be our datum. And then we know the radius is 0.1 meters. And so the simplified version of the equation, when we remove all of these terms that canceled out, it's just Z2 on one side of the equation, and on the other side is the rotational rate squared multiplied by the radius at 2 squared divided by 2g. So it's the rotational rate, omega, that we're interested in. So we just rearrange this algebraically for omega and get that it's 22.15 radians per second. And did it ask for radians per second? It just said, yeah, what is the rotational rate? And so 22.15 radians per second. You can see that I converted that over just for practice into revolutions per minute, RPM. So if you have radians per second and you want RPM, then you have to find out how many radians per minute there will be by multiplying by 60, and then convert from radians into revolutions by dividing by 2 pi radians per revolution. So it would be 211.5 RPM. That's the rotational speed. Any questions about this first part of the example, question A? All right, it said to find the radial acceleration experienced in the right leg. So if we know the right leg has an R of 0.1 meter and an omega of 22.15 radians per second, then the acceleration in the right leg, you can see, will be 49.05 meters per second squared. And what about the last part, the tangential velocity? So if we want to know v sub t, all we have to do is multiply the radius by omega. Up here, tangential velocity is radius times omega. So 2.22 essentially meters per second is the velocity of the water that is over here in the right leg and spinning around. So it's a pretty interesting equation, and in this case, since it was open to the atmosphere, then what happened is that the liquid level shifted and came into equilibrium as that U-shaped tube was rotating. Let's get some more practice with this just to help you to be prepared for the homework assignment and the upcoming exam that will be on the 17th of November. In this case, the tube is enclosed for this example. So what that means is that the liquid level isn't going to be changing due to the radial acceleration, but a pressure difference will arise. So you can see in this case where it's not rotating about one of the legs, it's rotating kind of maybe in the middle-ish. We know the distance from the axis of rotation over to one of the locations and the distance over to the other. And by the way, here it doesn't matter which one we choose as 1 or which one we choose as 2. There isn't any kind of directionality or a convention in which is which. So you're free to substitute L for location 1 and M for location 2, or vice versa. You can see on the 12.5 centimeters, that's telling us the elevation difference between the 2 points. And then here we're given the rotation rate of 25 RPM. Now, the first thing you should think when you see that 25 RPM is, well, I'm going to have to do a conversion because omega needs to be in radians per second. All right, so what I'd like you to do is with the known pressure of 2.75 at L, so here the pressure is 2.75 kilopascals, what will be the pressure at M if this tube is filled with an oil? So we have a specific gravity for the oil, and that's going to give you a different unit weight. This isn't just going to be the unit weight of water. You should use the unit weight of the oil that is inside of this tube. Okay, so hopefully you should start to see already some of the substitutions that are going to be made, and we're solving for the unknown pressure at M. So let me pause for a moment, give you some time to start crunching these numbers, and feel free to type your guesses into the chat box. All right, let me bring up the solution to this one so we can start looking at it together. All right, so I think it's a good idea up at the top next to a sketch to kind of start identifying all of the variables and values that we know. So for instance, the pressure here at location M is given as 2750 pascals. Assuming that this lower location at L is our elevation datum, then that means we're going to say ZL is 0, and then that makes the elevation at location M, 0.125 meters. And then here's our axis of rotation, so that the R that we're measuring is what distance is it from the axis of rotation out to the location of interest. So the radius of location L is 0.38 meters. The radius of location M is 0.133 meters. And then, of course, we already in the chat box talked about the unit weight. So if we multiply 0.85 by the unit weight of water, then you'll get the unit weight of this oil that is inside of the apparatus. And we are given the rotational rate in RPM, but what we want to know is how many radians per second this apparatus is passing through. And radians per second are going to be the same on the left as they are on the right. Now the tangential velocity is not the same because location L has a longer distance away from the center axis of rotation. But the number of radians per second is the same. So in our formula, there isn't an omega 1 and omega 2, there's just omega because it's the same. So here is the full version of the equation, and you can see that what I've done is rearranged it algebraically to solve for the pressure at M. So in order to do that, what we did is we moved the Zm over from the right to the left by subtracting both sides by Zm. And then we moved the third term from the right to the left by adding that term to both sides of the equation. So now it's moved over to the left side. And then the gamma, we have to multiply both sides by gamma in order to get just isolating the piece of M. Can you use a solver for these long equations on a Casio? I mean, you can definitely use your calculator, but I'm not sure if solver is the tool that you need here, because you're going to be solving directly. It's not like it's a numerical approximation or an implicit equation where the unknown is on both sides. Yeah, I don't mind you using any kind of, oh, I think I know what you mean. So you mean just like typing it in as it appears without rearranging it algebraically. And if you like, you can, but I think the problem with that is that, if you're taking shortcuts and just doing the solution in the calculator, then you're not communicating that to whoever's looking at your solution. So I think it's a safer strategy. If you make a mistake, the more work that you show on your paper, the more credit you can get in partial credit. And if you come back to it later and you're trying to remind yourself how you did a certain thing, having the solution written out in lengthy detail is going to be a better guide for yourself than if you just solved it in the calculator. So I won't insist on it, but I think it's good to make it as long and lengthy and detailed a solution as possible. Not unnecessarily lengthy, but to show all of the steps in between, I think there's value in that. Okay, so here is the form of the equation, and then starting to make the substitutions with the gamma, the omega. And by the way, it's, like the common mistake that I see when I'm grading exams is sometimes students forget to square omega. I don't know why, but it's just easy to forget that we need to square that term. So don't make that mistake. Be sure to always square the omega. So this is such a long equation, and I didn't start writing small enough soon enough that I had to kind of continue it down onto a second row. What we're saying is, here is the term of what's happening at location M, subtracting out what's happening at location L. The elevation at L is 0 minus the elevation at M plus the pressure at L. And so I've done that and then calculated the intermediate quantity for each, just so you can get an idea of like the relative magnitude of each term. And so, for instance, the rotation at location M, like how much of the ultimate pressure that you're going to be measuring came from this first term. You can see it's relatively small, 0.006 meters of head at that location. And the relative impact of the height of the liquid over at location L is larger. And then the effect of the elevation difference and the initial pressure. And so each one of those terms we have in base units of meters, just so we can see like where is the energy. And in the end, it should be that the pressure at M is 1339 newtons per meter squared. So this was different from the first example because the liquid level was constrained. And so the pressure was affected by the acceleration, but not the water level. So sometimes we'll use this equation to find how the liquid level deflects during a rotation, and other times we'll just use it to find how the pressure is changing. But the point is this is the third of our three equations that talks about how an acceleration affects pressure and elevation. And collectively, when we combine those two terms together, the pressure plus gamma z, that's the piezometric pressure. So acceleration affects the piezometric pressure. Any questions on the second example before we move on to the third and final for today? All right, so this is another one where the water is open to the atmosphere. So this U-shaped tube is open, and that's going to allow the liquid level to deflect. So look, where is the axis of rotation? You can see it's closer to the left leg. This axis of rotation is only 18 centimeters from the left leg, and it's 36 centimeters from the right leg. So when it begins, what we're seeing right now is like a before. After it starts to spin at 8 radians per second, then the liquid level isn't going to be the same anymore. Does anybody have an initial sense of on what side is the liquid level going to be higher? Will the water level rise on the left or on the right? You got a 50-50 chance if you just want to take a guess. Is the water level going to rise on the, okay, Courtney says on the right. Peter says on the right. Jacob says on the right. Trevor, right. Stephen, right. Regan says, oops. All right, so it is going to rise on the right, and the reason why is because it's further from the center axis of rotation, and so that on the right is experiencing more acceleration than the tube on the left. What our rule is that the pressure or elevation increases in the opposite direction of acceleration. And kind of a related corollary to that is that the more the acceleration, the more pressure or elevation change there's going to be. And so over here on the right leg, it's experiencing a larger magnitude of centripetal acceleration than the leg on the left. So since the acceleration is higher, then that's going to draw the liquid. The water level is going to lower on the left, and then it's going to rise on the right. So this is saying to find the equilibrium water elevations if it's rotating at 8 radians per second. Okay, now our strategy is we want to pick locations for 1 and 2 where we know things. If you have this printed out, what I'd like you to do is just maybe draw a little sketch of where the water level is changing when it starts to spin. And we don't know dimensionally yet how much it deflects. But what we know is that it's a little bit higher on the right and a little bit lower on the left. So just draw like a pencil, just kind of draw a line on the right that's above here, and then draw a little line on the left that's below. And what we're going to do is location 1 will be at the interface of the water and the air down here, and location 2 will be at the interface of the air and the water up here. And since we're doing it at the interface, one of the reasons why we selected that as the location is because that allows us to cancel out the pressure terms, because it's going to have just the same pressure as the air itself. So P1 will be 0, P2 will be 0. All right, now let's look at the third term on this equation. Omega is given to us already. It's even given in the units that we need it, radians per second. So how convenient is that? We know omega, the R is defined by this bottom dimension, the horizontal dimensions for the distance on the left, the distance on the right. Of course, G is just 9.81. Well, what it's saying is find the equilibrium water elevations. What that means is we want to know what is Z1 and what is Z2. We want to find out how far does it go down on the left and how far up does it go on the right. The only problem is we have two unknowns in the formula. Z1 is unknown and Z2 is unknown. So at first glance, it seems like we may be at an impasse. Does anybody have an idea of how we are going to solve this equation when we've got two unknowns? Any guess? There's got to be one more relationship that we can use. Spencer says they change in an elevation of x. I think you've got it, but what do you mean by that more specifically? How does the one goes up x and one goes down x? Exactly right. Yeah, Spencer's got it. So what Spencer realizes is that if the liquid level goes down some unit of distance, then on the right side, it's going to go up that same unit of distance. Just by inspection, looking at this tube, we can see it's a constant diameter. And so if the liquid level goes down on the left, it goes up on the right. And so one way that we could express that is we could say Z1 plus Z2 equals 0.36 meters. And so think about what I just said. Z1 plus Z2 equals 0.36 meters. What I'm saying is if we use the bottom of this tube as our elevation datum, right now Z1 is 0.18 and Z2 is 0.18. So collectively Z1 plus Z2 is 0.36 meters. And so water level goes down a centimeter on the left and it goes up a centimeter on the right. The sum of the Z values stay the same. And so now we have two equations, two unknowns. We've got our rotational flow equation and then we've got the elevation equation. So hopefully that's starting to give you an idea, and even if not, maybe you can start substituting in the values that you do know. But start substituting in R1, omega, G. I guess you don't need to know gamma because we're canceling out both of the pressure terms. But we want to find what is Z1 and what is Z2. And then that second equation that I said we're going to use, you substitute into this one, is that Z1 plus Z2 equals 0.36. So from that you can find Z1 is 0.36 minus Z2. Well, let's take a look here and see if your approach matches up with what I've done. I think it's a good idea to always include a sketch of the system with your solution. Even if you got terrible chicken scratch handwriting like me, it's still, there's something about drawing the system that helps you to really understand it better than if you just see the picture. And of course, also, it's a good habit to have a representation of the system on your solution, just so that you know it's there to refer back to later. All right, so when it's spinning, we don't know what the water level elevations are. The before photo that we have is before it started to spin. So it's not in equilibrium when the two elevations are both at 0.18 meters above the bottom leg. What we do know is the radius at both locations, and that the pressure will be 0 since we're going to have it at the interface. And even when it starts to deflect, what we're saying is that the one that we're interested in moves down with the water elevation. So we're going to say, by definition, location 1 is at the top of the water, and location 2 is at the top of the water on the right. So collectively together, they're 0.36 meters, or I rearranged it to say Z1 in terms of Z2 so that then I can substitute the right-hand side of this equation into our equation for rotational flow. So the pressures are both 0 at both locations. The rotational rate was already given. And the radius we know. And so here you can see what I've done is I've moved Z1 minus Z2 over to the left side of the equation, and on the right side equation is the difference of the omega squared times radius squared divided by 2g. And then substituting in our definition of Z1 in terms of Z2, now we only have one unknown. In this bottom equation, the only thing we don't know is going to be Z2. Everything else is a constant or a defined value. Let me zoom out a bit so we can get a look of all of it at the same time. Oh, this gets complicated, right? So omega squared divided by 2g, and then radius 1 squared minus radius 2 squared, and then divided by 0.36, I'm sorry, minus 0.36, and all of that is up in the numerator, and then divide by -2. Can you also solve for delta z and abstract and subtract and add that from 0.18 respectively? So you're asking, can you just move z1 minus z2 on the left side like this? Let's see, could we do that? Yep. Yeah, we could. So we could find the deflection between the two, and then you just assume that the deflection was even on the left and on the right. Yeah, I think that that would work. That would work. So what we're doing here is we're saying in absolute terms, what is the elevation on the left and the elevation of the right, and that's the water above the base leg. So it's the distance above the bottom leg there. Now the second part of this example asks, what if the rotational rate continued to increase? By the way, before we consider this second part, are there any other questions about the first one where we're finding the elevations at both locations? All right, so the second one, it was spinning at 8 radians per second, and what we saw is that there's very little water over on the left side. So think it's 33 centimeters on the right and 2 centimeters on the left. So the water level went up really high on the right, and it went down really low on the left. It went down, and so now out of the 18 centimeters that originally was on the left, when it's spinning at 8 radians per second, there's only 2 centimeters right now. So, and that was at 8 radians per second. So what happens if it spins even faster? So that's, you know, there's 2 centimeters of water on the left when it's spinning at 8 radians per second. If you keep increasing the rotational rate, what's going to happen to the water surface? It can't go down below the container. Anyone willing to speculate and guess what happens to the water surface as we continue to increase the speed of rotation?
It's going to travel to the right.
That's exactly right. Good, Casey. So what Casey recognized is that, the water level will go down and then it starts to go to the right. And so the water level is going to just keep going higher and higher and higher on the right side. But the water level on the left, it will go down, so then it's all the way drained vertically. And then what happens is the interface starts to move closer to the axis of rotation, and then it'll even go past it because the acceleration is higher on the left side. So what that means from a numerical standpoint, you remember the equation that we were using before was this. Z1 plus Z2 is 0.36. That's only true up to a point. Once you start spinning it fast enough that now the interface is down in the base leg, then Z1 will be 0. As soon as the water gets down here, Z1 is 0. But Z2 is going to be getting bigger and bigger and bigger because we're losing radius. And so this relationship is not true once you get beyond a certain rotation rate. And let me just illustrate for you, since we don't have a lot of time remaining. What happens, what if the rotational rate is 14 radians per second? Okay, so if we just substitute that into our original formula, like if we substitute that in here to this formula, then what you'd get is Z2 is 0.66 meters, and then that would give you a negative value for Z1. So that's impossible. The water level can't go lower than the base leg. So that tells you, okay, the water has moved into the base leg. So this earlier relationship we had of Z1 and Z2 no longer fits. So we have to have a different relationship. Instead of Z1 plus Z2 is 0.36, what we will say is that, think about this, take a look at this sketch. The water level is rising continually on the right, but what has happened is now the R1 is getting smaller. And so for every centimeter reduction in R1, there's a centimeter increase in elevation at location 2. And so this would be our new expression for the elevation at 2. It's going to be 36 meters because that's the height of the water when the water level starts to enter the base leg. So 0.36, so all of the vertical water is on the right, and now there's also additional water entering the right leg as the R1 retreats. And so if we look at the original dimensions for that, the original dimensions was the R1 was 18 centimeters. So what I'm saying is that the Z1 is going to be 18 centimeters plus the 0.36 if the R1 is 0. So this equation, I mean, it would take some thinking to figure out how you relate R1 and Z2, but this is the equation that does it. So that if we put in this faster rotation of 14 radians per second, and the original value for R2, and the unknown is going to be what is R1. And so we've got two equations and two unknowns. This is one of our equations, and our other equation is the rotational flow equation. So we substitute those two into each other, and you're going to end up with an equation that you have to find the roots for. There's a positive root and a negative root, and so if you use this negative root for R1, it tells you that the water has moved past the center axis of rotation. So when you're rotating at 14 radians per second, then that is going to cause the water level to rise up on the right side. So it's just kind of an interesting extreme. If you think about it continues to spin faster and faster, then it's no longer about the sum of the two vertical distances, but it's now about how much of the water in the base leg is shifted over to the right side as well. Okay, well, we are out of time. It's 12:15. I don't want to keep you late, but remember that homework 7 is due on Tuesday, and as you have questions on that, feel free to reach out. I'll be glad to help you out. Hope you have a good day. See you next time.